Okay, so thank you very much for the introduction. It's a great pleasure for me to talk in the occasion of Kavli IPMU's 10th anniversary event. Well, so this is partly joint work with Tabeshi Marwick, and I'm going to talk about some mathematical aspect of Kobackman buffer invariants. So these invariants were proposed by physicist Kobackman buffer about 20 years ago, but still, from a mathematical point of view, there are many things to do for the foundation, and I think that will give a complete understanding of such invariants also requires some new geometry, like a kind of virtual bidirectional geometry or so on, which I'm also talk about. Well, first let me talk about some basic stuffs. So, well, there are several invariants, quantum invariants, and on Calabi manifolds, and we are basically interested in counting curves on such varieties. So the basic object which we want to count are algebraic curves. So roughly speaking, they are one-dimensional complex algebraic varieties. In many cases, they are smooth, but sometimes they are not. And topologically, they are classified by the number of handles called genus. So the simplest one is called the rational curve. So this is just a sphere. It's a one-dimensional projective space. And the next simplest one, but still interesting one, is elliptic curve. So it is just a donuts-type surface. And there are more topologically difficult surface. So we are interested in counting such curves given algebraic varieties. So this is was important interesting problem in classical algebraic geometry. And also, this is also important in string theory, and the discovery of Miller symmetry predicts counting number of rational curves or higher genus curves into the solution with the solution of the differential equations of the Miller manifold. And the most interesting case for such theory is when the target variety is Calabi threefold. So this is defined as a complex threefold whose canonical boundary is trivial. So this is a famous example about counting rational curves on quintic hypersurface in P4. So if you consider a general homogeneous polynomial of degree 5, that is denoted by F, and if you consider its set of zero set of such equation, then this gives a complex three-dimensional space. And if you take such equation to be simply generic, then if you consider some lower degree rational curves inside this threefold, then it is known that there is only a finite number of curves inside in it. For example, for the degree 1 rational curves, so this is the number of lines inside such threefold. So this is computed at 2,875. And if you consider more higher degree curves, then we have more curves. And yes, especially for Calabi threefold case, in some cases, we can directly count the number of curves because in the ideal situation, they are expected to be only finite number of curves in it. However, such ideal situation is quite rare. In general situations, there exists infinite number of curves on a given Calabi manifold, Calabi threefold. For example, if you are given a curve inside Calabi threefold, and it also deforms, then you have a infinite many number of curves. So even if you fix the genus of the curve and the degree of the curve, then still it may be infinite number of curves. So in that case, the way to count these curves are to define some virtual counting of such curves. So the usual mathematical way to do it is to consider the set of such curves, and we compactify it to add some extra data on such curve, and use some intersection theory on such moduli space. However, such theories are not unique, and And there are several theories which give some curve counting on Kavli seafood, which are surprisingly to be equivalent. One of them is Gromov-Hitt invariant, and the other one is called Panda-Thomas invariant, and the last one is Bachmann-Buffer invariant, which I'm going to discuss. So this is a rough explanation about these three invariants, where Gromov-Hitt invariant, which I denote by GW, G beta. So this is, roughly speaking, now virtual number of curves together with maps to a given Kavli seafold. So such map is called stable map mathematically, and physically they correspond to world seed. Historically, well, around 1098, Bachmann and Buffer predict the existence of some integer valued invariant, where Gromov-Hitt invariant, by definition, they are rational numbers. So it's not ideal enumerative invariant. But Bachmann and Buffer predict certain integer valued invariant. Yes, geometrically they should count some pair of curves inside the Kavli seafold together with vector bundles on them. More precisely, they are one-dimensional stable shapes mathematically, and physically they are D2 branes. But well, there have been several issues in defining these invariants mathematically precise way. So its definition has been a kind of mysterious. But later, about around 2003, Morik, Nekrasov, Konkov, and Pandey, so they conjecture that these Gromov-Hitt invariants are also related to another integer valued invariant called, in the original paper they discussed in the framework of rank 1 Donaldson-Thomas invariant, but it is now equivalent to the so-called Pandey-Thomas invariant. This is, roughly speaking, pair of curves inside the Kavli seafolds and points on these curves. So these are mathematically called stable pairs, and physically they are D2, D0, D2, D6 bound states. So this is the last picture of these three. This is the last picture of the geometry behind these invariants. For Gromov-Hitt invariant, so this circle is, I assume this is Kavli seafold, and we are counting maps from this Riemann surface to this Kavli seafold. So the additional data of curves is a map from curve to the target space. And for the Pandey-Thomas theory, curve is embedded into a Kavli seafold, but we have additional data of points. And on the Bachmann-Buffer side, we have embedded curve together with vector bundles on that curve. But of course, this is the ideal picture, and in general, this picture is more complicated. For example, you may have some curves which have complicated singularities, and the vector bundle on Bachmann-Buffer side, so it may have also complicated singularities. So the issue is that, Gromov-Hitt invariant and PT invariant, they are mathematically very established invariants. We have a well-defined notion of virtual fundamental cycle on the modular spaces which define them. But however, about the Bachmann-Buffer invariant, mathematically its definition is has not yet been clear. So there are many unsatisfactory points for the current definitions. But of course, there have been several proposals, which I will review later, but about these invariants. The ideal case is, yes, when we consider a modular space of pairs like curves together with vector bundles on them. If that modular space is non-singular, then there is no problem. But if the V1 modular space has singularities, then usually such singularity is quite bad. This means that, for example, it does not fit into the framework used in birational geometry, like KLT, log canonical singularity, or so on. So it is even not reduced. So this means that it may be possible that every point is singular. So in that case, where the proposed definition, yes, before our paper with Davish-Malvik, so they do not match with the mathematically established invariant, Gromov-Fit invariant or PT invariant, except the genus zero case. Yes, in the genus zero case, we have a well-defined definition. But in the higher genus, where, yes, this is still a difficult problem. But before discussing about the mathematical definition about Markov invariants, where I'm going to discuss about the revision of Van Hypen-Thomas invariant and Markov invariant, where both of them are some sort of sheaf theory. And for me, this revision is much more accessible to me. Where roughly speaking, but still, where both of them are some sort of sheaf theory, but still its revision is quite mysterious to me. And in ideal situation, where this kind of correspondence should be an analogy of the following well-known phenomena, that if you fix a smooth projective curve of genus G, and if you consider the symmetric product of that curve, so this is a smooth projective variety, so you can compute its topological Euler number. So that the generating sheet of such topological Euler number is easily computed as a power of q plus 1, and it is described as a Poincare polynomial of the Jacobian of the underlying curve C. So this peak 0C is a G-dimensional complex torus. So its Poincare polynomial is just a power of the Poincare polynomial of the sphere. So yes, so these two sheets are closely related in this way. But there is some discrepancy of this term. Yes, in the genus zero case, the correspondence of PT invariants and GB invariants, well, this is explained by the so-called wall-crossing phenomena of Bridge stability conditions in derived categories of coherent sieves. So this is the result which I found just after I came to IPMU about 10 years ago. And after that, well, yeah, I studied this idea, and yes, this idea led to the proof of the so-called rationality conjecture of the generating sheets of Van Hypen-Thomas invariants and many other properties of Donaldson-Thomas type invariants. So Donaldson-Thomas invariant is a kind of invariant which count sieves or object in the derived category on Calabi seafold, and it includes PT invariants. Right, but however, yeah, again, I emphasize that in higher genus, the even mathematical definition of Markov invariants has not been clear. So as I thought, well, in ideal situation, it may be something like Poincare polynomial of Jacobian. So this means that we use some cohomology theory of the moduli space. But if the moduli space has singularities, then the usual cohomology theory does not behave well. So you have to find some refined version of cohomology theory for some single moduli space. So there are some history toward mathematical definition of such invariants. Well, of course, the first one was due to Bachmann and Boffa. So they physically proposed integer valued invariants that is equivalent to Gromov-Fit invariants. And they also proposed that, well, in the ideal situation, like when the moduli space is indeed non-singular, then you can consider its usual cohomology and considering some d-algebra action on it and taking some character to get invariant. But as I said, well, the issue is when the moduli space has quite bad singularities. And yes, one candidate of considering such a cohomology theory for singular variety is to consider the intersection cohomology of moduli spaces of one-dimensional sieves. So that approach was taken by Hosono, Saito, Takashi in 2001, and they defined the Markov invariant using the intersection cohomology of moduli space of one-dimensional sieves. However, still, it's not satisfactory because well, the intersection cohomology only captures the topology of the moduli space, and it does not capture the scheme structure on the moduli space. or virtual structure on it. So even in genus 0, the Hosono-Saito-Takahashi definition does not fit into Kumho-Huijten or PT invariants. So later in 2006, Sheldon Katz proposed the definition of genus 0 invariants using the virtual fundamental cycle of the moduli space of one-dimensional sieves. And by the work of Kai Behrendt, where the definition of Katz can be interpreted in terms of certain micro-local geometry. That is, where using that observation, maybe the recent paper by Kim Lee, they constructed a certain parallel shifts of vanishing cycles on the moduli space of one-dimensional sieves. And they take the associated group of the weight iteration and then apply some V-algebra action on it by following the analogy of Hosono-Saito-Takahashi approach to give some invariant. So before our paper, so Kim Lee paper was the latest one. But however, in our paper with Tameshi Mavic, we found that the Steve Kim Lee's definition is not correct. So there are two issues. First, their definition contains some artificial choice of data, which I will explain later, but it is called orientation data. This is a quite important piece of defining such invariants. And more battery, where we also find some example where Kim Lee's definition does not match with Kumho-Huijten or PT invariants for any choice of such orientation data. Well, yeah, the issue is a bit technical point, but where they take parallel shift vanishing cycle and then take its weight iteration and then take associated group to make it coming from pure Hodge module. So that makes then to have a V-algebra action on its hypercohomology, but we're taking associated group due to some information, so that that is a reason why such counterexample happens. So in a joint work with Tameshi Mavic, we modified the Kim Lee's definition and defined the buffer invariant from the moduli space, which I denote by M, one-dimensional stable shifts on Kavli seafold whose homology class beta. Yes, the key ingredient, we modified the Kim Lee's definition in two points. First, instead of considering real algebra action on the hypercohomology of some parallel sheaf, instead we take a character formula of SA2 product, SA2 action. So without taking associated group of the weight iteration. And another piece of modification is we take a kind of orientation, we impose some condition on orientation data of M, which I call Kavli orientation data. So now I'm going to explain about these terminologies about vanishing cycles and orientation data. Yeah, so to explain it, maybe I have to back to the work by Toen and his collaborators on the derived enhancement of the moduli space of stable sheaves. So yes, by the recent development on the derived algebraic geometry, we know that where the moduli space of stable sheaves on Kavli seafold has derived enhancement, which also has a so-called shifted symplectic structure. So it's not a usual symplectic structure, but so the symplectic structure has some grading, and the grading is just -1. And the existence of such symplectic structure imposes some strong constraint on the moduli space of stable sheaves. And using such result, Dominic Joyce's group showed that the moduli space M has a so-called D-critical structure. So yes, so it's a bit technical notion, but this means that but the existence of such D-critical structure implies that the moduli space M is covered by some open subset U, which is written as critical locus in some smooth schemes V. And this chart is called D-critical chart. So locally, the moduli space looks like a critical locus of some function on some smooth scheme. And also the existence of global shifted symplectic structure also remembers how to glue this chart. And yes, so roughly speaking, the existence of D-critical structure implies that where it is locally written as critical locus, and also this function f also have some growing data globally. And yes, if you have a scheme with the critical structure, then at least locally you can construct a sheaf of vanishing cycles on each open chart. The problem is whether we can glue this locally defined parallel sheaf to a global parallel sheaf. So this is a non-trivial problem, but once you choose a certain additional data, which are called orientation data, so this is defined to be some growing of the square, where this is a certain square root of some bundle, line bundle on the moduli space M. So locally, we have a line bundle on U given by the square of the usual canonical bundle on V, and the existence of the critical structure implies that this local line bundle grew together to give a global line bundle that is called virtual canonical line bundle. And the orientation data is a choice of a square root of such line bundle. So this is the proposed definition. So from the moduli space of one-dimensional stable sheaves, so there is a so-called Hilbert Char map. So this is char X is a moduli space of effective one cycles on X. And this map is defined by sending a one-dimensional sheaf to its support. So this is something very similar to the so-called Hitchin map of on the moduli space of Higgs bundles. So our definition of buffer invariant is to characterize such invariant by this identity. So if you fix orientation data, then you can push forward it to char variety and then take parallel cohomology and then take its Euler characteristic. Then we know that this parallel sheaf is self-derived. So the left-hand side is uniquely written in the form of the right-hand side. And if we know that this hypercohomology of the vanishing cycle has some SU2 product SU2 action in suitable way, then such where the resulting invariant can be characterized in this way. So the point is that instead of considering the V algebra action, we characterize invariant by this identity. But still, there is one subtlety. So the third point of this definition is a choice of a correct orientation data. So yes, we know that there is orientation data, but yeah, it's not canonical. And we import the condition on orientation data so that it is a pullback from the char variety under the Hilbert Char map. And we call such orientation data as Kavli orientation data because in that case, this Hilbert Char map is something like a virtual Kavli fibration. And we conjecture that such a choice always exists. And the point is that in general, the definition of buffer invariance depends on choice of orientation data. But if we take it to be Kavli orientation data in this definition, then it is independent of orientation data as long as it is Kavli. So in order to check that our invariant matches with other invariant, yes, I compare it with PT invariant. Where let Pn beta, so this is Van-Thomas invariant, which, roughly speaking, virtual counts of genus G curves with homology class beta and n plus g minus 1 point. Then the conjecture identity is formulated in terms of the generating series in this way. So this is precisely the analog of the identity which I described before about the Euler number of the symmetric product of curve and the Poincare polynomial of its Jacobian. So the main theorem of my paper with Marwick is that if you consider the total space of canonical line bundle on smooth projective surface, and if you take the curve class beta to be irreducible, this means that the homology class beta is not written as sum of other effective curve classes. Then in this case, the previous Van-Thomas Waffle conjecture is true. So we have some identity of the generating series. Yes, and in this case involves many examples where the moduli space has singularities. So yes, still proving the previous conjecture in general is difficult, but in this case, yeah, we can prove that. Yes, another third point is about the dependence of our invariant with stability condition. So far, I didn't talk about a choice of stability condition, but there are some flexibility of its choice. Namely, if you take some element, b plus I omega, so this is an element in the complex-wide ample cone of X. So then, by fixing such stability element in the complex-wide ample cone, then we have the notion of stability condition. So the stability condition depends on a choice of b and omega. And if you have given this data, then we have the well-defined notion of a semi-stable object or stable object for one-dimensional sieves. And a priori, it's possible to define buffer invariant from any choice of stability conditions, so which I denote by ng beta sigma. But yeah, but indeed, well, the resulting invariant is indeed independent of a choice of stability condition sigma. So this means that we don't have to take care about the choice of stability condition in defining these invariants. So another corollary, yes, as a corollary of this result, where we have a so-called Floop transformation formula of buffer invariants. That is, if you take a Floop between Kavli seafold, then we have the identity of buffer invariant. Where such identity is expected from the such Floop transformation formula of Gromov-Fit invariant and also Van Thomas invariant. So we also have an expected answer for this. But for me, rather than the result of this, I think that the proof is also interesting. Well, roughly speaking, in the course of during the proof, I showed some structure theorem of the wall crossing of moduli space of one-dimensional sieves. Namely, if you consider some variation of stability conditions, which I note by M plus is some moduli space with some stability condition in a chamber. M0 is a moduli space, coarse moduli space, which writes where the stability condition writes on a band on a wall. And M minus is a stability condition, M minus is a moduli space, which corresponds to stability condition after crossing the wall. Then we have such a diagram. Then, well, in general, as I thought, these moduli spaces have quite bad singularities. So we cannot expect about a nice geometric property of these moduli space in general. But what I proved is this is locally written as a more accessible way. That is, for each point in the coarse moduli space, I have this diagram so that where this is a Floop between smooth varieties, and also there is a map from the downstairs to the compact number field. And this diagram is locally written as critical locus of these two functions, as the D-critical schemes. So this is something like a Floop. So analogy of the Floop for D-critical schemes. So yes, I think that this kind of observation will lead to some sort of new rational geometry. So this is last slide for future perspective. So I call a diagram like M plus to M0 to M minus as a D-critical Floop. So this is a virtual version of a Floop. So this is locally written as locally on the downstairs, written as a critical locus of some functions, and the ambient space is related by Floop. And such notion can be generalized to other birational transformations like D-critical flips, D-critical divisory contractions, or so on. So this indicates that the D-critical schemes, that is schemes together with the D-critical structures, they may fit into new type of birational geometry, which I'd like to call as D-critical birational geometry. And yes, so on Kavli seafold, there are many other wall crossing phenomena. And in this wall crossing, I can show that the geometry behind such wall crossing fit into this D-critical birational geometry. And I believe that developing such geometry leads to some geometric understanding of wave crossing on Kavli threefolds. So far, the wave crossing on Kavli threefold are only done in the numerical level or cohomological level by considering the Donaldson-Thomas invariant or cohomological Donaldson-Thomas invariant. But it also leads to some more geometric understanding of wave crossing, and which I think also generates Bondar-Orlov, Kawamuta's D-equivalence and K-equivalence conjecture for D-critical schemes or so on. So that's it. Thank you very much.